In this section, we look at the second and third advantages of feedback versus open loop control. The first one we look at here is sensitivity, which has to do with how well does our controller work if the parameters of the plant are not exactly what we thought they were. For example, on the motor, if that J term, the inertia, was not exactly what I thought, or if the L term of the inductance or the R term of the resistance was not exactly what I thought, when I designed my controller, how does the system work? And the second one that we're going to look at after that is dynamic tracking. So let's look at sensitivity. We already looked at steady state gain, and we designed an open loop controller so that we would have a steady state gain of 1.0 in the absence of disturbance. And so we now look at, well, how does this gain change if some parameter in the motor changes? For example, what if the constant A in the numerator changes? So one way of thinking about that is to say, well, the A that I had in my equations gets replaced by A plus delta A. Well, the gain of the open loop system then is the original gain plus some change in gain because of this change in the constant versus what I thought it was. And the original gain was K open loop times A, but in reality the total gain is going to be K open loop times the real value of A, which is A plus delta A. Now remember that we designed the open loop controller, we designed KOL to be equal to 1 over A. So I put that into the expression as 1 over A times A plus delta A and distribute through, and I get a gain of 1 plus delta A over A. So this here is the gain error. I designed my controller thinking that I would have a gain of 1, but in fact it's a little different from that. It's different by a factor of delta A over A. That's in absolute terms. In relative terms, kind of like a percentage-like term, we could think of, well, what is the change in gain divided by the gain that I designed for? So the change in gain, I'm different by this delta A, designed for A, and we can think of that then as 1 times delta A over A, where we have, this is our sensitivity factor. How much does the gain change versus the original gain is some number times how much the plant changes divided by the original plant number, and that constant is what we call the sensitivity. A sensitivity of 1 means that a 10% change in A gives us a 10% change in the gain. It's a 100% correlation between those. Evaluating the closed loop system goes along similar lines. You have to think about it in a little bit more careful way, but we can still do it. The steady state gain of the closed loop system, we said, was this. And so the gain of the closed loop system plus whatever change in gain there is, so the revised gain when A changes, is what I get when I substitute A with A plus delta A in the two places that it occurs. Now, we can then use calculus to figure out, well, what is the little delta gain in terms of the delta A, and by the law of the total differential, the partial change is equal to the total differential times the partial change. And we can then take this, we can divide both sides of this expression, take this, divide that by GCL, and I can then divide this also 1 over GCL. And then I can also multiply this side by A over A, and by manipulating things we have I can have on the left-hand side the change in gain divided by actual gain, which is in correspondence to that term there, what I wanted. And I can also have the delta A over A, which is the correspondence with this term I had over here. So everything that's left over is the sensitivity. And combining everything that's left over gives us this term right there. So the sensitivity you can think of as the change in gain divided by the change in parameter in total terms, but also normalized by the original gain and the original parameter to get it in a fractional sense. Instead of an absolute sense, it's a relative sense. And that's our sensitivity, and we give that the name S for sensitivity sub A, the parameter that we're comparing sensitivity for, and then the gain, what we're evaluating the sensitivity of. So we can calculate this. So I have to compute this derivative term, dGCL by dA, to do it. And I have an expression for the CL, so let's plug that in. So dCL by dA is the derivative with respect to A of the closed loop gain, which is what I had from before. And here we're using the quotient rule of calculus because we see that A is in both places. And the quotient rule says the derivative of a quotient is equal to the denominator times the derivative of the numerator. So derivative of a KCL with respect to A is just KCL. And then minus the derivative of the denominator, which is minus KCL times the numerator, all divided by denominator squared. When we do that, in the first term, I multiply 1 times KCL, I get KCL, and I multiply a KCL by KCL, and I get A times K squared, but over here I have a minus A times K squared that cancels that, and that goes away. So the differential term in our calculation required the quotient rule, and we're done. And we substitute that in here. I want the sensitivity. We said that's the differential term, which we just calculated, times A divided by the actual closed loop gain. So there's my A divided by actual closed loop gain, which is K, A times K over 1 plus A times K. And that multiplies K over 1 plus AK squared. This term cancels one of those. That term cancels that, and the A cancels that. So I'm left with, in the numerator, 1, and in the denominator, one of those. 1 over 1 plus A times KCL is the sensitivity. So we've gone through the math, and now we have to think about the math. What is the math telling us? Well, we found out that the sensitivity of the open loop gain to the parameter A was equal to 1.0. The sensitivity of the closed loop gain to A is equal to 1 over 1 plus A KCL. And remember that we designed the closed loop gain so that this term would be very, very big. So if I divide 1 by a very, very big number, I'm going to have a very, very small number. And that means that our sensitivity is very small. So this is the second advantage to feedback. We're lowering the sensitivity to modeling error by a factor of 1 plus A times KCL. Now again, I think this should make some intuitive sense. If you learn to drive one automobile, that experience somehow translates to almost any other automobile very well. Now, how is that? Well, it's feedback. You've learned that when the car is going too slowly, you press the accelerator a certain way and it speeds up. When it's going too quickly, you release pressure from the accelerator and you slow down. Now, if you tune that open loop for one vehicle and you drive a different vehicle, then, oh my goodness, you're in for a wild ride. You're going to be going much faster or much slower than you thought. But because you've learned to use feedback, you're continuously looking at the speedometer and you're saying, oh, this car is more aggressive than the one I'm used to driving, so I don't need as much accelerator pedal pressure in order to accelerate and so forth. And so you're using feedback in order to be much less sensitive to the differences between different automobiles, and so you're able to drive many of them. This is an idea that we also call robustness. A controller is called robust if you can change different values in the plant and still have the controller work acceptably well. A controller is fragile if that's not the case. And so we would say that an open loop controller is generally fragile, but a feedback controller can be designed to be very, very robust, and that's a huge advantage. The third thing that we look at is dynamic tracking. So we've looked at steady state errors. As time goes off to infinity, as time gets very big, we can have very, very good tracking with the feedback system and rejection of disturbances, and we can have low sensitivity and so forth. But what about the dynamics, the transient response, if you will, of the system? The open loop system, we noticed, had poles in the transfer function at roots of that equation, tau 1s plus 1 times tau 2s plus 1, and those are at minus 1 over tau 1 and minus 1 over tau 2. The open loop system did nothing. Those were the original poles of the motor, so if the motor was not as fast as we wanted it to be, then, well, it's still the same slow motor. If it was too fast or too jittery or too much overshoot or too much something, well, it's still what it was. The open loop system did absolutely nothing to change the transient response. We just designed that one gain factor to somehow tune the steady state response so that the error would be small. We also noted in the last section that when we employed feedback, the poles of the closed loop system were different, that they were the roots of this other equation, tau 1s plus 1 times tau 2s plus 1, plus A times KCL. And we can expand that out, and then we can use the quadratic rule to look for the pole locations, and here is what it is. But we really can't go much farther than that without having numeric values of tau 1 and tau 2 and A and KCL. But the big picture here is that the poles are at different places. They are not at the minus 1 over tau 1 or minus 1 over tau 2. And the only way that they would be is if A times KCL was equal to 0, which is maybe easier to see here. If that was equal to 0, then my denominator terms would be exactly the same. But you can also go through the math of the quadratic equation and see if that is 0, then that can be solved. And the roots are at minus 1 over tau 1 and minus 1 over tau 2. Now, this is a cause for rejoicing and it's a cause for concern. This is the power of feedback, but with power you have to be careful because you might, if you employ it without knowledge, you can cause more damage than you end up curing ills. So feedback moves poles of the system. The system then may have faster or slower response than it did originally. The system may be more damped or less damped. In other words, it may be more oscillatory or less oscillatory. I guess it's the other way around. More damped is less oscillatory, less damped is more oscillatory. I might even move the poles of the system into a region where they become unstable, which is the right half of the S-plane, as we saw when we looked at the S-plane in the last chapter, that poles in the right half have a time domain response that becomes unbounded. And in fact, often a high closed-loop gain, KCL, will result in instability in real-world systems. So in our example in this section, in the previous section, we said, let's just design A times KCL to be big. Well, we have to be careful. In this case, it actually will work, but it will not work in every case. A high gain can result in instability. And you know this from practice also, because I think every one of us has been in an auditorium, and when they are adjusting the sound system, they turn the gain of the sound system up too high, and all of a sudden the sound that is emitting from the loudspeakers is picked up by the microphones in a loud enough way that gets amplified, and it causes a feedback loop. And it's even called feedback when the speaker system starts screeching at you at its resonant frequency. And how do we stop that? Well, we turn the gain of the amplifier down until this stops. So having a high gain in a feedback loop can be good, but it can be awful. And so we need to learn how to design it. For this particular example, I stuck some numbers in and looked at some step responses. And so for a low value of closed-loop gain, we get this black step response. And we see that it's nice and smooth, which is probably desirable, and that it settles down in about 10 seconds to its steady state value, and that's actually pretty close to 1. So the idea is I'm setting R of t equals 1 of t, and I'm seeing how well the motor tracks that. And after about 8 or 10 seconds, it's tracking it quite well with very little steady state error and no drama getting there. Well, I can crank up the gain and I can try high values of KCL, and that's what I did with the blue line. And I simulated the same input to the system, and this is the output that we get. We get something that has a lot of overshoot and a lot of ripple, and it does settle down, maybe a little faster than the other one, maybe not much, but a little faster, and it has maybe a little better steady state error. You can see here the blue line is closer to 1 than the black line is. But this big overshoot here, you have to look at what is the application, and can the application tolerate an overshoot like that in the response. Sometimes the answer is yes, but many times the answer is no. And so we have to tune the value of KCL in our design in order to get the kind of overshoot that we want. At this point, we don't really have tools to do that besides trial and error, but as we go along, we will develop those tools for how to tune the controller to give good response the first time we turn it on. So here, in this example, we see the first potential downside or disadvantage to feedback, and that is that if the controller is not well designed, it might make the plant's response worse than it was to begin with. And so designing controllers is a major focus of the rest of this course and follow-on courses. If you remember the end of Chapter 1, we listed that just at this university we have 9 particular courses in feedback control. So it's a very broad subject area, and there are even other areas that we haven't designed courses for yet. So this is not a trivial task, but we will be able to design really good controllers by the time you're done with this course. So we can get a really good start toward improving the dynamic response with a closed-loop controller, like the one we looked at. But if we think a little bit harder than simply using a gain factor, an amplifier in our feedback system, we can do even better than that. So the next topic we're going to look at over a couple of sections is what is called a PID controller, and that stands for proportional integral derivative, and we'll see why it's called that. And then we'll return after that to exploring some advantages of feedback.